just so you know, we do have class today. What is it, President's Day? So I guess the president has the day off, right? The rest of us have to work. Um, so, um, exam one, the class average was a 70. It's like 5 points higher than the rest of the classes. So y'all are the best one. But I suspect it might be because I let y'all use your phone for a calculator. Currently, I have to keep everything exactly in sync with all the other classes, so you'll have to use a calculator from now on the exams in class. Okay, trying to save y'all some money, but apparently a scientific calculator doesn't cost that much these days. It's like $10, right? So if you don't have one, borrow one from somebody, right? And I guess start using it so you are used to using it for the exams. Okay. Apparently, it didn't help that much. You know? All right. Last semester, the class averages were like a 90 because students were taking their exams outside of class, right? So like pre-COVID, the average were like 65, 70. The next semester, once COVID hit, they were like 75. The next semester, they're like 85. And then last semester, they're like 90. So we had to start having exams in class, but students were clearly just cheating their asses off. Okay. So welcome back to reality. There was an exam retry, but they didn't know that we had changed our exam date from Wednesday to Friday so that we could get that review in. So they shut down the link to sign up for it kind of early. You know, they did reopen it like right after class, but apparently y'all didn't get the chance. You know, we didn't have any of my students there. Of course, it was on a Saturday, and who wants to take an exam on a Saturday? But in the future, you will be able to sign up for the exam one or exam two and exam three retries. They will always be on the Saturday after the exam. Okay. So you have to sign up for, there is limited seats. So you do have to sign up in advance. All right. So right after the exams, I'll post a link in the announcements and you can use that link to sign up for a retry. The retry is a written exam. You get a piece of paper, scratch paper, the exam, and a pencil and your calculator, and that's it. All right, and they watch y'all like hawks. And the written exams, I don't think it's any more difficult than the in-class exam, but the in-class exam is multiple choice, right? So if you don't know anything at all, you still can just guess, right? It's really hard to do on a written exam. Okay? So because y'all didn't get the chance to do the retry, I talked them into letting me replace your exam one with your final exam grade if your final exam grade is higher than your exam one grade. And so that way, if like, you didn't make it to the exam or something, you still have a chance. You can still do well this semester. You're not totally out. Fair enough? All right. Figure that's more than fair. You're gonna have to take that written exam on a Saturday. I didn't want to grade exams all day, but I did. Okay, so that's notes on exam one. This week we're doing 11.7 and 11.8. All right, so your guided notes, and written work, whatever it's called, is due next Monday, as usual. Okay, so take a look, make sure that they're showing up. I think I set them up correctly, so they should be showing up there in Blackboard for you. Okay. So let's get rolling here. So the chain rule. Chain rule allows us to basically deal with more complicated stuff. You'll have what? The power rule, the product rule, of course the quotient rule, and now the chain rule. What you do if you have a function inside of a function, all right? We know what to do if a function is multiplied by one another or divided. What if you have a function inside of a function, Then you use the chain rule. So it basically allows us to like peel it like an onion, okay? So here's an example. It's composite functions, a function inside of a function. So let's see. Let's just look at an example. It would be easier for me to tell you. So if you have a function inside of a function like this, g of f of x, all right, the derivative, right, the derivative of a function inside of a function is going to be the derivative, the outside function, times the derivative of the inside function. Okay? So what does that mean? To you? Here's some examples. Okay, see, find each of the following. Okay, so before we get to the calculus, they just want us to make sure we understand how to evaluate stuff. G of f of 4, okay? We have G, here's f. What's f of 4? F of 4 is where you replace x with 4. So, replace x with 4. 2 times 4 is 8, minus 1 is 7. Now G says do this to it. So we replace the x with a 7. This is just a review on composite functions. So this is 21 plus 5 square root of 26. Okay. 4, notice we've switched the f and the g, f of g of 4. So g of 4, here's g, it says replace the x with a 4. Let's see, this is 12 plus 5 is 17. So f of the square root of 17, f says do this. So replace x with the square root of 17. So notice these are not equal, not the same, right? F of g of 4 is not the same as g of f of 4. Okay. Here's another example. G of minus 2. Okay, here's our g. It says replace x with a minus 2. So what is this? The square root of minus 1. Well, that's an imaginary number, right? And so in here, we're not dealing with imaginary numbers, right? In any other math class, we're like, it's just a number like any other number. It's a complex number. Fine. Yes. I can't hear you. You're gonna have to yell at me or sit closer. Make each of the equations equal to one another. Well, this is equal to this. I've just replaced f of 4. This is f of 4, right? I just replaced the x with a 4, right? That's all we're doing is plugging it in. Yeah, we're just evaluating this function. All right. I mean, let's see here. G of f of x. All right. What is f of x? F of x is 2x minus 1. So g of that, here's g. It says replace the x with the input. This would be the square root of 3 times 2x minus 1 plus 5. So that's g of f of x, right? Just terms of x. But f of g of x, the g is the square root of 3x plus 5. And then f says multiply the input by 2 and then subtract 1. There's g of f of x and f of g of x, right? They're different functions, right? You're plugging one into the other. Okay, so like this is f of x, this is f of x, and this is f of x. Okay. So all this is review. We're just evaluating the function. You can have a function inside of a function, right? What that is. Normally we just say, here's a function, and we call it f. So here we're trying to break it down to show you that all functions are composites of other functions. The first example they did was like the cube root of x or something, right? Well, this is x to the 1/3. I could say f of x is just x, and g of x is the cube root. Yeah, see a little, put a squared in there. Okay, so this would be x to the 2/3. Okay, so we could say f of x is x squared, g of x is the cube root of x. So we would see, well, g of f of x would be g of x squared, would be x squared 1/3. So when you see a function like this, you could think of it as x squared inside of a cube root, okay? So when you see something like this, you could say, oh, here's something, we're multiplying it 2 and subtracting 1, all right? So you could take any function and break it down into a whole composite of functions. So before we even get to calculus here, we need to just review our basics. So here's two functions. Find g of f of x. Well, f of x is 4x plus 1. G says take your input, square it, multiply it by 2, and then add 5 times the input. That's g of f of x. F of g of x, g says 2x squared plus 5x. Okay? Well, f says take 4, multiply that times your input, and then add 1. Okay? So these are not the same. Okay? Point there. All right, here's an f and a g. What is g of f of 2? Well, f of 2 is replace the x with a 2. This is what? 6 minus 2 is 4. And g says take your input, subtract 1, take it to the 5th power, so it's like 3 to the 5th. Whereas f of g of 2, g of 2 would be 2 minus 1 to the 5th power, which is just 1 to the 5th, which is 1. And f says take your input, multiply it by 3, subtract 2. All right, two functions, f of g of x. G is x squared plus 5x plus 1. Copy that. Now f says take the square root, the input, and add 4. Now, g of f of x, the f is square root of x plus 4. And then their input, g says take our input, square it, then take 5 times our input, and then add 1. Can you handle this? One function inside of the other. That's all you're doing. What do they want? Express this function as a composite of two functions. Okay, well, let's say I say f of x is x cubed plus x squared minus 5. This thing's to the 4th power, right? So I'm going to do g of x is x to the 4th, okay? So this guy, h of x, is going to be g of f of x, right? We're gonna put this in, and then this thing says square it. I mean, raise it to the fourth power. All right, makes sense? So we want to be able to go the other way as well. We want to see this and think of it as not just a function, it is a function, but you can think of it as the composite of two functions. Okay, here's another one, okay, b. So if I said, okay, I'm going to think about the 4x squared plus 5 as a function, and then I got to deal with the square root, so I'm going to deal with the square root as a function. So this dude would be g of f of x, right? There's the f of x, and then we want to square root that stuff, right? I'm sure you don't get it backwards, right? Because dyslexia going on, right? Finally, the chain rule. So there's the chain rule again. You have a function inside of a function. The derivative is the derivative of the outside, evaluated at the inside, times the derivative of the inside. You're basically just peeling an onion if you want to think about it that way. Let's look at an example. Once we have this down, we're done with derivatives, and then we can start doing this stuff backwards called integrals. Here's a function. What is it? Y is 15x squared plus 1 to the 1/2 power, right? So y prime, we have stuff to the 1/2 power. So first we're going to use the power rule. The power rule says multiply by the exponent, subtract 1 from the exponent, right? That's what the power rule says. But we're not done. This stuff in here is not just x. We have to multiply it times the derivative of the stuff on the inside. The derivative of the stuff on the inside would be a 30x. Okay? We've been hiding some stuff from y'all, basically. When you have the derivative of f of x, right? We said this is f prime of x, right? We never put that it's times the derivative of the stuff on the inside, right? We never said that. That's because this is just 1. That's why we never bothered writing it or even mentioning it. But we've always been doing the chain rule, okay? We've been doing this the whole time. We just hid it from you. Blah, 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 blah. Let's write this out in more detail. So dy dx, right, is the derivative of 2x to the fourth 3 to the 1/2 power. So all I did was rewrite this as a 1/2 power, right? This is my y. So this is 1/2 2x to the fourth plus 3 to the minus 1/2 power times the derivative of the stuff on the inside. So I'll have this. And the derivative of the stuff on the inside here would be 8x to the third. You want to write it out step by step by step here, okay? All it is you deal with the outside function first, and then you multiply by the derivative of the stuff on the inside, right? And I could say, okay, times the derivative of x with respect to x, because we had an x here, but we never bother writing this. Later on, that's going to be important because we're going to have multiple variables. We're going to have x's and y's and z's. Okay? Here is the alternative form. This is the same thing as what we had a while ago, but in terms of dx's, okay? So if y is a function of u and u is a function of g, all right, that means y is f of g of x, okay? We would say dy dx equals dy du du dx. Notice the du's cancel, you have dy over dx, all right? Technically, you can't do that in mathematics, except for when functions are real pretty. When you're dealing with complicated stuff, it's more complicated than that, all right? Because these things aren't just, these things are infinitesimally small. So when you're dealing with infinitesimally small stuff, you can't always just treat it like it's algebra, right? But in here, we can treat it like it's algebra because our functions are real nice and simple, okay? For now, you just want to be able to take basic derivatives, and it'll get more complicated later. Dy dx. Okay, here's y. So dy, x. Dy dx, we're just putting this operator in front of what y is. Y is 3x squared minus 5x to the 7th. Okay, so all I did was replace y with what y was. So this says, deal with the outside function first. This would be 7, this stuff, to the 6th power. Now times the derivative of the stuff on the inside. We still have this. Now the derivative of the stuff on the inside here is 6x minus 5. All right. With practice, you'll be able to do this in one step, basically. You'll just be able to write down the answers. Okay. Oh, here they want us to use, look at their solution here. They use the alternative version of it, right? Let's look at their analysis here. Here's their function. Y equals 3x squared minus 5x to the 7th. Look at their version. So they're saying this is u to the 7th, okay? Where u is 3x squared minus 5x, okay? So here's how you do it with the alternative one. I'll work through it instead of just reading you their answer here. If you want to do substitution, well, like where u is this stuff, it's u to the 7th. So dy dx, right, is the derivative of u to the 7th dx, right? So this would be 7 u to the 6th times the derivative of u with respect to x, and the derivative of u with respect to x, oh, let's see, I can replace it. Oh, I want to do it. It's 6x minus 5. But u is this stuff. The same answer. All they're doing is they're saying, let's take all this stuff and we're going to call it u. Okay? And that makes it apparent. We're taking the derivative of this. It's just the power rule. 7u to the 6th, but you have to multiply by the derivative of the stuff on the inside. Okay? See, before, if you had x to the 7th, you would take the derivative. This would be 7x to the 6th times the derivative of the stuff on the inside. But this was always just 1. So we never wrote it. We never mentioned it. That makes sense? It's always been there. It's always been equal to 1. Well, now it's not 1 anymore. for example. Here's y. All right, so the derivative of y with respect to x, the derivative with respect to x, 10, 2x squared plus 1 to the fourth. You can always pull the 10 out, right? We're going to do this step by step. So this would be 4. That would give us a 40. And we have 2x squared plus 1 to the third, right? Multiply by the exponent, subtract 1 from the exponent, times the derivative of the stuff on the inside. We still have this. The derivative of the stuff on the inside would be a 4x. Of course, you could just look at it and go 4, right, y prime, 4 times 10 is 40. Subtract 1 from the exponent, now multiply by the derivative of the stuff on the inside, right? You can do this in one step. That's what you want to be able to do. You want to be able to look at it and write the answer down. Not that hard. You put that one. So the generalized power rule, this is just the power rule with the chain rule, right? This isn't something new, all right? If you have a y equals u to the n, all right? Y prime, the n, subtract 1 from the exponent, and then multiply by the derivative of the stuff on the inside. We already did this example, okay? So this isn't anything you need to remember. You know the power rule and the chain rule, all of that is doing both of them. All right, this guy, here's y prime, again, y prime is the same as writing dy dx, okay? We have to do the power rule. We have 2. Subtract 1. That would just give us the first power. We're not going to write it. Times the derivative of the stuff on the inside. B. Here's y. So y prime is multiply by the exponent. Subtract 1 from the exponent. Now times the derivative of the stuff on the inside. Yeah? We're just going to do this over and over and over again like 100,000 times. All right, here, y prime, multiply by the exponent, subtract 1, now multiply by the derivative of the stuff on the inside. This one, this is really what, 9x plus 2 to the 1/2 power. So the derivative, multiply by the exponent, subtract 1 from the exponent, now multiply by the derivative of the stuff on the inside. Derivatives are really, really easy. This is the last rule, the chain rule. Now you can take the derivative of anything, no matter what it is. Right? We will want to be able to take derivatives of other functions like logarithms and exponentials. We'll do that next, but it's not hard. All right, so this one, y prime, multiply by the exponent, subtract 1 from the exponent, multiply by the derivative of the stuff on the inside. Derivative, multiply by the exponent, subtract 1 from the exponent, now multiply by the derivative of the stuff on the inside. F prime, multiply by the exponent, subtract 1 from the exponent. Now multiply by the derivative of the stuff on the inside. Multiply by the exponent, subtract 1 from the exponent, and multiply by the derivative of the stuff on the inside. Power rule, chain rule, power rule. Can you handle this? All right, is it sinking in? Okay, get those. See, the hard part of calculus class is integrals. It's doing the derivative backwards. So if I give you a function and I say, okay, this function is the derivative of y. So it's just doing derivatives backwards. That's really hard. Even though crazy derivatives are so easy, right? Why is doing it backwards so hard? It's like multiplying two numbers together is really easy, right? But if I give you a huge number and I promise you it's the product of two prime numbers, so there's only those two numbers multiplied to give you that number. I say, I promise it's a product of two prime numbers. What are the two numbers you multiply to get this number? That problem is so hard, all of our internet encryption is based on it. That's how all our encryption works. So you can see like some things are easy to do one way, but the opposite way it could be almost impossible to do. So integrals are hard, but these are easy. Y prime, multiply by the exponent, subtract 1, now multiply by the derivative of the stuff on the inside. All right, y prime, multiply by the exponent, and subtract 1 from the exponent, now multiply by the derivative of the stuff on the inside. All right, y prime, that's what dy dx is. Okay. Here's some common mistakes here. The common error is to forget to multiply by g prime. Multiply by the derivative of the stuff on the inside, right? When using the generalized power rule. Okay. Another common mistake is to write the derivative, taking the derivative first. So a common mistake like up here would be instead of just subtracting 1 from the exponent, right? This hasn't changed. Some students will take the derivative of that and put it in there instead. They would have 8x in there instead. You got to take it one layer at a time. So don't make those common mistakes. And you won't if you just practice. All right, now we have a function times a function. Let's be a little more careful here. This we have to use the product rule, right? For y prime, remember this is a u, you have u times v, and you take the derivative, it's the derivative of one times the other, plus the derivative of the other, is a 1. Remember that? Okay, so if we take the derivative of 4x, that's just 4, right? So it's the derivative of the first one times the second one, plus the first one times the derivative of the second one. The derivative of the second one is 5 multiplied by the exponent, subtract 1 from your exponent, and multiply by the derivative of the stuff on the inside. So if we want to write this out, dy dx, we have the derivative of the first one times the second one plus the derivative of the second one times the first one. So this is just 4. Forgot this guy. And then the derivative of this is, well, 5 times 3x plus 5 to the 4th times times the derivative of the stuff on the inside. And then we still got a 4x here. It's all the same. The derivative of this stuff is what? 3. And we still got our 4x. Okay. All right. 3, 5, 4x. 3, 5, 4x. The same answer, right? Should be able to do this in one step, though. Here's one with the quotient rule. So what was our quotient rule? It was, if you have u over v prime, it was over v squared, v prime u minus u, no, u prime v. There we go. So there's a quotient thingy, right? So the derivative, we're going to have the thing on the bottom squared. We have the thing on the bottom times the derivative of the thing on the top. The derivative of the thing on the top is 7, subtract 1 from the exponent, multiply by the derivative of the stuff on the inside. And we have minus the stuff on top times the derivative of the stuff on the bottom. Well, that's just 1. That's the algebra. Right here we had to do the chain rule and taking the derivative of the thing on the top. All right, here we're gonna have to use the product rule, right? I can't multiply this in. I mean, I could square this dude out, right? If I squared this dude out and then multiplied by that, I wouldn't have to use the chain rule, right? But the chain rule's faster, right? So y prime, right? We have the first function times the derivative of the second. So multiply by the exponent, subtract 1 from the exponent. I'm not even going to write the 1. Times the derivative of the stuff on the inside. The derivative of the stuff on the inside is just 1, so I'm not going to write it. Then we have plus the second function times the derivative of the first. All right, we could write that out if we wanted to. dy dx is the derivative of the first function times the second function plus second function, that's the derivative of the second function, now times the first function. The derivative of 9x is 9. The derivative of this is 2, x plus 1 to the first power times the derivative of x, which is 1, times 9x. And it's just doing it step by step by step. Is 1 y prime. So we have two functions here, right? So we have the first, now times the derivative of the second. So we got to do the power rule. I'll multiply by the derivative of the stuff on the inside. And then we have the derivative of the first times the second. Am I skipping too many steps? I figured you guys should see how to do it in one step and then also do it with multiple steps, right? For some reason, I think dragging out and all these multiple steps kind of obfuscates what we're trying to do there. So if I wanted to write this out, dy dx, we have the first function times the derivative of the second plus the derivative of the first times the second. These parentheses here are really important, right? That's a thing, right? This derivative is applying to what's in the parentheses here, right? This derivative. So this is getting multiplied on to this, right? I'm not taking the derivative of that, no. It's just the derivative of that and then multiplying it by that, okay? So the parentheses are really important. I like to put square brackets next to round brackets in my days in programming. I don't like round brackets next to round brackets. You get lost in, parentheses, right? Let's see, we'd have a minus 3x. And now the derivative of this guy is 3, right? We multiply by the exponent, subtract 1 from the exponent. Now multiply by the stuff on the inside. This guy here is just a minus 3. And then we have stuff. Right? I could color code it for you. I think that's a bit of overkill. Did we do that one? I don't know what we just did. What did we do? Checkpoint 8. Okay. Checkpoint 9. All right, this one, we could cube this thing out and divide everything by 11x, right? And then we wouldn't have, we could just use the power rule. But let's do the quotient rule here. Y prime. So we're going to have the thing on the bottom squared. We have the thing on the bottom. Now times the derivative of the top. So that would be a 3. Subtract 1 from the exponent. Multiply by the stuff on the inside. We have to subtract. And then we have the top times the derivative of the bottom. The derivative of 11x is just 11. All right, this guy, the quotient rule. We know we're going to have the thing on the bottom squared, and we start off with the thing on the bottom. Thing on the bottom times the derivative of the top. The derivative of the top is a 7. Subtract 1 from the exponent. Multiply by the derivative of the stuff on the inside. The derivative of this is just 1, right? We just have an x. And then we have minus stuff on the top times the derivative of the bottom. The derivative of the bottom is just 6. Consider that we may rewrite the following rational function in the product form. Okay, we could rewrite this like that, right? This is just to the minus 1 power. So we can either use the quotient rule or the product rule, right? We never actually needed the quotient rule. We could have always just take the thing on the bottom and wrote it as a minus 1 and then use the product rule. So if we do that, if we use the product rule here, oh wait, they want us to use the quotient rule first. Okay. It's the thing on the bottom squared, the thing on the bottom times the derivative of the top minus the top times the derivative of the bottom. C, use product rule. Okay. We're going to use this version of it, right? If we use the product rule, we have the first function times the derivative of the second. The derivative of the second is a minus multiplied by the exponent, subtract 1 from the exponent, times the derivative of the stuff on the inside. So that's the first times the derivative of the second. And then we want the second times the derivative of the first. Derivative of that is just 3. So you can see that thing squared. Here that thing is squared. Here you have it to the minus 1, but you can multiply the top and the bottom by that again and combine those into one fraction. These are in fact the same. Okay? Right, this is the same as putting this down here. Right? Same as putting this down here. and then I can multiply the top and the bottom, and then combine these, right? So times that, and they are the same thing. So with the chain rule, you don't even need the quotient rule anymore. Okay, use any method. Well, let's use the quotient rule. 5x plus 3, the bottom squared, bottom, derivative of the top, minus the top, and the derivative of the bottom. We wanted to, y prime. If we wanted to do it the other way, we do first function times the derivative of the second, right? Power rule, chain rule, then plus second function times the derivative of the first. Those are equal. 3 minutes. So that's another reason why I can't do it step by step, is because there's no way I could cover an entire section in one class period. Finance. A generous aunt deposits $20,000 in an account to be used by her newly born niece to attend college. The account earns interest at a rate of R% per year, compounded monthly. At the end of 18 years, the balance in the account is given by this. So this is your 1 plus R over N to the NT. Y'all remember compound interest formula? Okay. Find the rate of change of A with respect to R. That means find the derivative of A with respect to R. So we will call this A prime. Since there's only one variable here, we can call it A prime, right? Right? If there's more than one variable, A prime, we don't know what that means, okay? So we have 20,000. So we'll do the power rule. We multiply by the exponent, subtract 1 from the exponent, times the derivative of the stuff on the inside. The derivative of that is just, this is just a number times R. That's it. So that's A prime. So if you want A prime of 1.5, with all of this, where we replace R with 1.5, and the others you just plug in the different numbers. Once you get your A prime, boom, now you can evaluate it for whatever you want. So that's the rate of change of A with respect to R. That's what that means. Blah, 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 blah. So, there's some more examples of that. This we're going to have to use right here next time. We're going to have to focus on this. This we're going to pick up next time. Marginal revenue product. It's going to be something I always forget. I have to relearn it every time, but it has to do with partial derivatives. Okay. So notice we have n's, derivative with respect to n, and also the derivative with respect to x. So these are different rates of change, right? Like, how does the revenue change if you hire more employees, right? How does the revenue change if you manufacture more product, right? So there's lots of things you can change, and when you change it, you want to know how it changes everything else, right? So we need to be able to deal with more than one variable here, right? So this is going to be the fun part. We're actually getting into business. So that's it for today. We'll see y'all on Wednesday.